Let's talk about the universe for a bit. You think you understand it, right? You've seen pictures of it. You know there are stars, planets, galaxies. You know there's a vast space out there, so large it's almost infinite. But try answering one very simple question for me. In a universe that contains hundreds of billions of stars just in the Milky Way and thousands of billions of other galaxies, how many intelligent civilizations do you think exist? It sounds obvious, doesn't it? A lot. Maybe millions. Maybe countless. Telescopes like the Kepler Space Telescope have shown us that planets are everywhere, and the conditions for life are not that rare. So by simple logic, intelligent life shouldn't be the exception. But this is where things start to get uncomfortable. If that's true, then where are they? Why, after decades of listening, searching, and waiting, have we still received nothing? No signals, just silence. And the thing is, that silence isn't meaningless. It's saying something, and maybe what it's saying is much more frightening than us not hearing anything at all. If just the Milky Way alone contains hundreds of billions of stars, then it's almost inevitable that there are billions of planets with Earth-like conditions. And you don't need to be a scientist to see that the probability of intelligent life appearing multiple times is extremely high. In 1961, Frank Drake tried to turn that intuition into mathematics with the Drake equation, a simple tool to estimate the number of civilizations that could be communicating in the galaxy. And even if you choose very conservative numbers for each factor, the result is still not one or two, but potentially thousands. But then you run into a problem. In 1950, during a lunch at Los Alamos, Enrico Fermi asked a question so short it was almost uncomfortable. Where is everybody? That question became the Fermi paradox, because it points out a contradiction you can't ignore. If civilizations exist, they should have left traces. And we have searched for those traces seriously. Starting in 1960 with Project Ozma, we began listening to the universe with radio waves. And organizations like the SETI Institute have spent decades scanning millions of frequencies, looking for any signal with structure that would indicate intelligence. But after more than 60 years, the result is still zero. No confirmed signals, no evidence. And at this point, you're forced to face an uncomfortable truth. Either our estimates are wrong, or something is preventing civilizations from existing or communicating. And that very silence is the most important data we have. So let's consider an idea that I think is both simple and extremely dangerous cognitively. Because once you understand it, you can never go back to your old way of seeing the world. It's called the Great Filter, a concept popularized by Robin Hanson. And basically, it doesn't require complex assumptions or sci-fi technology. It just says something very straightforward. In the entire chain of events, from inanimate matter to a civilization capable of communicating between the stars, there is at least one step that is extremely difficult, to the point that almost all systems fail there. And that's why you don't see anyone. It sounds simple, but slow down a bit, because the scary part isn't in the idea itself, but in the details. Let's start with the most basic thing we know, Earth itself. This is the only laboratory we have. And it is not a normal example. It may be an extreme exception. Life on Earth appeared about 3.5 to 4 billion years ago, very early after the planet had cooled enough for liquid water to exist. But that was only simple life bacteria, single-celled organisms without complex structure. And the interesting thing is that for nearly the next 3 billion years, almost nothing changed significantly. Pause on that number for a second. 3 billion years. That's a period much longer than the entire history of animals, of dinosaurs, of humans, all added together. And throughout that entire time, life did not advance the way you usually imagine. It just existed. It persisted. It did not explode into intelligence, did not develop technology, did not build telescopes to look back at the universe. It just was there. Then about 600 million years ago, something happened that we call the Cambrian explosion, an event in which complex multicellular organisms began to appear at a relatively fast pace by geological standards. And if you're thinking this was an inevitable step, then no, that's exactly the problem. We don't know why it happened. We don't know what conditions actually triggered it. And that means it could be one of those filters. Maybe billions of planets have simple life, but almost none advance beyond that step. But let's keep going. Multicellular organisms appeared. Then it took hundreds of millions more years to develop complex nervous systems. And then hundreds of millions more years to have creatures with behavior flexible enough to be called intelligent. Dinosaurs dominated Earth for more than 160 million years, but they didn't build technology, didn't develop science, didn't send signals into space. And only after an asteroid hit Earth about 66 million years ago, wiping out most of life, did a small branch of mammals get the chance to develop in a different direction. And from there, it took tens of millions more years to lead to humans. Now look at the final number. Technological intelligence, the kind that can broadcast radio signals, has only existed for just over 100 years. 100 years, compared to billions of years in the history of life. That means if you took a photo of Earth at any random point in the past, you would almost certainly not see a technological civilization. You would see bacteria, or fish, or dinosaurs, but not something capable of communicating. And this is where things start to get serious. Maybe the problem isn't that life doesn't exist, but that it rarely reaches the stage where you can detect it. And that's exactly the logic of the great filter. It doesn't require assuming that life doesn't exist. It doesn't require assuming the universe is empty. It only requires assuming that there is one step in this chain that is extremely difficult. And if you multiply the probabilities of all the steps together, you can end up with a number that's almost zero. Not because each step is impossible, but because all of them together at the same time is too hard. But this is the part I want you to pay the most attention to, because this is where the idea shifts from interesting to terrifying. Where does that filter? That's the only question that really matters. If the filter is behind us, if the hardest steps have already happened, if the formation of life, multicellular evolution, intelligent soul of these were extremely rare events that we have already passed, then the good news is that we are in a special position. We could be one of the very few civilizations in the galaxy, or even in the universe. That sounds lonely, but it's not dangerous. It just means we are rare. But if the filter is ahead of us, then the whole story changes completely. In that case, what you're looking at is not an empty universe, but a universe full of unfinished stories. Planets where life began, evolved, developed, maybe even reached technology and then stopped. Not because they didn't want to continue, but because they couldn't. Some limit appeared, some technology got out of control, some event happened, and the process stopped before they could spread to the stars or send signals that we could receive. And what really makes me uncomfortable is that we have no data to know which side of that filter we're on. From inside the system, everything always seems fine. Life evolves, technology develops, society expands, and you can believe that trend will continue. But Earth's history shows that nothing guarantees that. Dominant species can disappear, ecosystems can collapse, and there is no law that says technological intelligence is a stable endpoint. So when you return to the original question, where is everybody? Maybe the answer isn't that they're too far away or that they're hiding, but simply that they're no longer there. And if that's true, then the silence of the universe is not an emptiness, but a signal. A very clear signal, but not in the way we expected. It doesn't say, we are here. It says, no one lasted long enough to say anything. So if you set aside the worry about the filter for a moment and just look at the raw numbers that modern science provides, you'll see that the initial picture is almost indisputable. And honestly, it even feels quite comforting, because it tells you that we cannot be alone. According to analyses from the Hubble Space Telescope team, the observable universe may contain about 2 trillion galaxies, not a few dozen billion as we once thought, but a number dozens of times larger, and each of those galaxies contains anywhere from billions to hundreds of billions of stars, just like our Milky Way. That means if you start multiplying these numbers together, you quickly realize that the total number of stars in the universe is a figure that's almost impossible to grasp intuitively. But stars are only the beginning of the story, because what matters more is what orbits around them. In the past few decades, thanks to missions like the Kepler Space Telescope, we have discovered that planets are not rare exceptions, but a natural consequence of star formation. And many studies indicate that about 20% of sun-like stars may have planets in the habitable zone, where liquid water can exist. If you stop here and do a very rough calculation, you'll see that even in our own galaxy, there could be tens of billions of planets with conditions similar to Earth. And if you expand that to the entire universe, the number of these potential Earths becomes so enormous that trying to count them loses all meaning. And this is the point where your intuition starts to kick in. Because when you look at a system with so many opportunities, you are almost forced to conclude that life cannot be a one-off event. It must be a common phenomenon, perhaps even inevitable. You don't need to assume that every planet has life. You only need to assume that a very small percentage of them may develop life, and an even smaller percentage may develop intelligence. And even if those percentages are extremely small, multiplying them by the enormous number of planets will still give you a number that is not small at all. This creates a very strong, almost inevitable expectation that the universe must be full of civilizations, from simple forms of life to technological civilizations that can observe the universe just as we are doing. And not only that, if you continue thinking along these lines, you'll realize that with the universe being about 13.8 billion years old, there have been many opportunities for civilizations to arise millions, even billions of years before us. That means if even a small portion of them developed technology long enough, they could have spread throughout the galaxy, or even beyond their own galaxy. And this is when things become almost impossible to ignore, because if a civilization has a time advantage of millions of years over us, then in principle, they could have had enough time to leave clear traces in the universe, whether radio signals, artificial structures on a stellar scale, or any form of intervention in the astronomical environment that we could observe. So when you put all of this together, from the enormous number of galaxies, the number of stars, the number of planets, the probability of life existing, and the vast amount of time the universe has existed, you see that the natural, almost unavoidable expectation is that the universe must be overflowing with life and intelligence. Not just a few scattered bright spots, but a dense network of civilizations at many different levels of development. And if you stop here, you would feel quite confident in that conclusion, because it is built on numbers we have measured, observations we have confirmed, and very basic probability logic. And then you return to reality, and that's where things start to become uncomfortable in a very specific way, because all those reasonable expectations we just built don't disappear. They're still there, but they collide directly with a single fact we cannot ignore. We see nothing. It's not we haven't seen it yet, but we have searched and still see nothing. There's not a single signal confirmed to come from intelligence beyond Earth. Not a single data set with structure clear enough to rule out natural sources. Not a single repeating pattern you can point to and say there was intent behind it. Search programs like the SETI Institute have spent more than half a century doing something very simple in concept but extremely complex, technically, listening to the universe. They don't just listen once. They listen continuously, over and over, expanding the frequency range, increasing the sensitivity of the equipment, and improving data analysis algorithms. Because if there is an artificial signal, a signal carrying information, a signal designed to cross the distances between stars, then in principle we should be able to recognize it. But when you look at the results, not individual events, but the entire body of data accumulated over many decades, you see something very uncomfortable. Everything fits natural background noise. There are signals stronger than usual. There are unusual fluctuations. But when you examine them more closely, they can all be explained by familiar physical phenomena, or they simply don't repeat. And in science, something that doesn't repeat is not evidence. It's just a question mark. You might say we could just be looking in the wrong place, or not long enough. But the problem is that we're not searching in only one way. If civilizations exist and have developed to the point where they use energy on a large scale, they cannot be completely invisible. A simple idea is that if a civilization wants to make maximum use of their star's energy, they might build structures around it, a concept often called a Dyson sphere. And even if they don't build a complete sphere, if a significant portion of the light is absorbed and re-emitted as heat, you would create a signature in the infrared spectrum that modern telescopes could detect. Surveys from missions like WISE have searched for exactly those kinds of signatures across hundreds of thousands, even millions of stars, and the result is still the same. No convincing evidence of stellar-scale engineering. No systematic missing energy traces. No unusual distribution patterns you would expect from a civilization using energy at that level. And if you think a little further, you'll realize that a civilization doesn't even need to want to communicate in order to be detected. Just by existing and operating on a large enough scale, they would leave traces. Self-replicating probes, planetary scale engineering projects, or simply changes in the astronomical environment around them. All of these could create indirect signals. But observations from advanced tools like the James Webb Space Telescope, combined with large ground-based observatories, still show a universe that looks very ordinary. Stars form according to patterns we understand. Planets orbit them in predictable paths. Clouds of gas and dust move according to familiar physical laws. There is no standout technological disturbance, no sign of a system that has been altered on a large scale. And this becomes especially important when you remember that we don't need thousands of civilizations to see traces. We only need one, a single civilization that developed millions of years before us, if capable of expanding, could have left traces we could detect at the galactic level. But we don't see that. So this silence is no longer a minor detail you can brush aside. It becomes the center of the problem. It is not lack of data, but data itself. It is an observational result, just like any other result in science, and that means it needs to be explained. You cannot simply say maybe they're too far away, because distance does not explain the complete absence of all kinds of traces. You also cannot say maybe they don't want to communicate, because even if they are intentionally silent, large-scale technological activities would still leave signs that cannot be completely hidden. And you certainly cannot say we haven't searched enough, because we have searched enough to begin seeing a trend. And that trend is very clear. The universe, at least at the level we can observe, shows no evidence of the presence of intelligence beyond Earth. And this is where things shift from interesting to alarming. Because when you have a clear contradiction between what you expect from the numbers and what you actually observe, you are forced to consider the possibility that some basic assumption is wrong, or that there is an important factor you haven't accounted for. And when you go back to everything we've talked about before, from the enormous scale of the universe to the probability of life existing, you start to realize that the problem is not whether there are enough opportunities, but what is happening after those opportunities are created. The silence is not the absence of information, it is a form of information. It says that with all the opportunities the universe provides, the final result we observe is still nothing remarkable. And if you accept that as a factual reality, then the question is no longer why don't we hear anyone, but what happened to all the civilizations that should have existed? And if you start wondering whether we simply haven't searched enough or haven't searched in the right way, then that's when you need to look more closely at how we have actually searched. Because this is not a half-hearted or speculative effort, but a serious scientific program that has lasted for many decades, with increasingly powerful technology and increasingly sophisticated methods. Let's start with radio telescopes, because that is the most direct way to listen to the universe. For many years, one of the most powerful tools we had was the Arecibo Observatory, before it collapsed. And this instrument was capable of picking up extremely weak radio signals from distances of thousands of light years. The idea here is very simple. If a civilization develops technology advanced enough to transmit signals, especially structured signals like information-carrying waves, and those signals could cross the distances between the stars and reach us. But listening is not as simple as turning on a radio and waiting, because the universe is not a quiet environment. It is full of noise, from cosmic microwave background radiation to natural radio sources like pulsars, quasars, and other physical phenomena. So scientists don't just listen. They scan a very wide spectrum of frequencies, from a few megahertz to several gigahertz, looking for signals with unusual characteristics, such as narrowband signals, repeating signals, or signals with clear mathematical structure, things that are difficult to be produced by natural processes. And they don't do this just once. They repeat it, cross-check the data, filter out Earth-based interference, and confirm whether the signal repeats or not. That is why events like the WOW signal in 1977, although very interesting, are still not considered evidence, because it never appeared a second time. But the search for extraterrestrial intelligence is not limited to radio waves. As technology advanced, we began to expand our approach. One of the important directions is the search for biosignatures, that is, biological signs in the atmospheres of exoplanets. This idea is based on a very basic principle. Life, especially complex life, changes its environment. On Earth, the presence of oxygen in the atmosphere is a direct result of photosynthesis by living organisms. If you look at Earth's atmosphere from a distance, you will see a clear chemical imbalance, a sign that biological processes are taking place. So scientists have begun using telescopes to analyze the light passing through the atmospheres of distant planets, looking for molecules such as oxygen, methane, or ozone, things that could indicate the presence of life. And this is where modern tools become extremely important. Instruments like the James Webb Space Telescope allow us to observe in the infrared wavelength with unprecedented precision, enough to analyze the atmospheric composition of planets that are tens or even hundreds of light years away from us. This means that for the first time in history, we are not just guessing about extraterrestrial life. We can begin to test it with real data. In addition, there are other indirect methods, such as the search for technological signs, also known as technosignatures. These could be anything from structured laser signals to unusual changes in the light of a star, or even energy patterns that do not match natural processes. Modern projects do not rely on just one type of data, but combine multiple sources, from radio, optical, and infrared, to theoretical models of how a civilization might use energy. And what is important is that all these methods are getting better over time. The sensitivity of the instruments increases, the range of observation expands, and data processing capability improves thanks to artificial intelligence and advanced analysis algorithms. In other words, if there is a signal that is strong enough, clear enough, and close enough, our ability to detect it is getting higher and higher. And that is exactly what makes the problem more uncomfortable, not more comfortable. Because as our technology advances, as we expand the scope of our search, as we increase the sensitivity of our tools, you would expect that we would start to see something. It doesn't have to be a clear message, just a small sign, an unexplainable anomaly, something that makes you stop and say, this is not normal. But so far, that has not happened. What we see is a universe that is becoming more detailed, clearer, but still without any traces of intelligence beyond Earth. And here is the important point. This silence is not due to a lack of effort, but the result of a very large effort. We have searched in many different ways, across many different frequency bands, with many different tools, over a long enough period of time to begin drawing conclusions. And that conclusion, at least for now, remains unchanged. No confirmed signals, no technological signs, no direct evidence. So when you hear someone say, maybe we haven't searched enough, you need to understand that that statement is not wrong, but it is also not enough. Because science does not wait for absolute certainty, it works with probabilities and trends. And the trend we are seeing is a silent universe, not because we are not listening, but because there seems to be nothing to hear. You may begin to doubt something that previously seemed too simple to question, the assumption that life must be common. Because if we don't see any signs despite searching very seriously, perhaps the problem is not in the search, but in the initial premise itself, that life may be much rarer than our intuition suggests. When we talk about life, especially life as we know it, we are really talking about a very specific set of conditions, not just one or two factors, but a chain of physical, chemical, and astronomical constraints that must all be satisfied simultaneously. Let's start with the most basic, liquid water. All life on Earth that we know of depends on water in its liquid state. And this is not a minor detail, because liquid water only exists within a very narrow temperature range. And that leads to the concept of the habitable zone, a region around a star where the distance is just right so that water is neither completely frozen nor evaporated. But even this condition alone greatly limits many star systems, because if a planet is too close, water turns into vapor. If too far, it freezes into ice. And both of those states are unfavorable for the complex chemistry that life needs. Observations from the Kepler Space Telescope have helped us quantify this better, and the results show that only about 20% of Sun-like stars have planets lying in the habitable zone. It sounds like a lot, but remember that this is only the first step in a long chain of conditions. A planet in the habitable zone does not mean it actually has life. It only means it is not ruled out from the start. After that, you need to consider the internal structure of that planet, because to maintain a stable environment, the planet needs a strong enough magnetic field to protect its surface from cosmic radiation and stellar wind. Earth has this, thanks to its molten iron core spinning inside, creating a magnetic field that surrounds the planet like an invisible shield. Without this magnetic field, high-energy radiation from space could gradually destroy the atmosphere, strip away the water, and make the surface harsh for life. And we have a very clear example of this: Mars. About 4 billion years ago, Mars may have had liquid water on its surface, maybe even rivers and lakes. But when the planet lost its global magnetic field, probably because its core cooled, it also gradually lost its ability to retain an atmosphere. The solar wind blew the gas molecules out into space, and over time the water disappeared, leaving behind a cold, dry planet that is almost devoid of life. This shows that if just one element in this chain is missing, the entire system can collapse. But even if you have water, a magnetic field, and are in the habitable zone, you are still not done. Complex life does not just need conditions to exist. It needs stability over a very long time. On Earth, life has existed for billions of years, and only after a very long period did complex forms of life appear. This requires a relatively stable climate, without prolonged extreme fluctuations, and without being constantly destroyed by astronomical events such as large impacts or extremely strong radiation. And this is where things get even more difficult, because planetary systems are not simple systems. They are affected by many factors, whether the planet's orbit is stable, whether there are giant planets like Jupiter that help clean up dangerous asteroids, whether the planet's axis of rotation is stable, and even the presence of a large moon like our moon, which helps stabilize the axial tilt and therefore the climate over long periods. If you start listing all these conditions, you will see that each factor has its own probability, and when you multiply them together, the overall probability can decrease very quickly. This does not mean that life is impossible. Clearly, we are here. But it does mean that life, especially complex life, may not be as common as we once thought. And when you return to the original question, this starts to make sense. Maybe the problem is not that civilizations are hiding or don't want to communicate, but simply that there are very few places where all the necessary conditions are met for life to develop to that level. Maybe the universe is not completely empty, but it is sparse in a way we never imagined. Oases of life may exist, but they are too far apart, too rare, and too fragile to form a network that we can easily detect. And if that is true, then the silence we observe is not a deep mystery that needs a complicated explanation, but a natural consequence of a universe where the conditions for complex life are extremely rare. But even if you accept that, there is still a problem, because even a very small number of civilizations, if they last long enough and develop far enough, could still leave traces that we could see. But if you stop at the conclusion that life is simply rare, then you are overlooking a very important part of the problem. And that is how probability works when you have an enormous number of trials, because in science you cannot just look at a small number without placing it in the context of the entire system. Let's go back to what we know. Not with vague intuition, but with the numbers that astronomy has provided. Even before the modern estimates, we knew that our galaxy, the Milky Way, contains hundreds of billions of stars. And if you accept that planets are a natural consequence of star formation, then you are talking about an enormous number of planets, not hundreds or thousands, but billions. And this is just one galaxy. When you look further out, you see that the universe contains countless galaxies, each one a similar system. And although we don't need an exact number, what matters is realizing that the total number of opportunities for life to appear is extremely large. Now, suppose you say that the probability of complex life forming on a planet is extremely small, maybe 1 in a million, or 1 in a billion. It sounds very small, almost negligible. But when you multiply that probability by billions or trillions of opportunities, you no longer get a small number. You start to get a significant number, even a large one. This is not speculation, but basic probability logic, and it does not depend on your feeling about what seems reasonable. You can imagine this with a simple example. If you flip a coin once, you cannot predict the outcome. But if you flip it millions of times, you know that both results will appear many times. And if you increase the number of trials to billions, then the chance of any particular outcome appearing only once becomes extremely unlikely. The same applies here. If the universe provides an enormous number of opportunities for life to appear, then even a very small probability will lead to many occurrences. And when you add the factor of time, the problem becomes even clearer. The universe has existed for billions of years, and during that time, stars have formed and died through many generations, creating new planets and new environments for life to develop. This means that if life can appear, it not only has many places to appear, but also has a lot of time to do so. And this is where scientific intuition begins to push back against the idea that we are unique. To accept that we are the only civilization, you have to believe that in the entire universe, with all those opportunities, all those time spans, all those physical and chemical processes, there is only one single place where everything combined in exactly the right way to create intelligent life. This is not impossible, but it requires an extremely rare chain of events happening in succession without any repetition anywhere else. In science, we tend to be skeptical of explanations that require such coincidences, not because they cannot be true, but because they are not the simplest or most natural explanation. And this leads to another problem. Even if you accept that life is rare, you still have to explain why we don't see any traces of other civilizations. Because if there are only a few civilizations in each galaxy, or even just a few in the entire universe, then at least one of them could have appeared millions of years before us. And if a civilization has such a time advantage, it could have developed technology far beyond what we have, and could have left traces that we could observe. So the problem is not only how many civilizations exist, but also how long they last, and what they do during that time. So when you put all of this together, you realize that the life is rare hypothesis may explain why we don't see many civilizations, but it does not explain why we don't see any civilizations at all. It reduces the number but does not bring it to zero. And when you need an explanation that brings that number close to zero, you need a stronger mechanism, something that not only makes life rare, but also makes the long-term existence of civilizations extremely difficult. And that is when you start to think that maybe the problem is not whether life appears or not, but what happens afterward, something that causes most systems to never reach the stage where we can detect them. Let's start from the very first point, where everything is still pure chemistry, when Earth was just a hot rock with oceans gradually forming over time. The process of moving from inorganic matter to a system capable of self-replication, what we call life, or abiogenesis, is still a great mystery. We have hypotheses from the primordial soup to chemical reactions on the surface of minerals, but we have never fully reproduced this process in the laboratory. And that means we don't know whether it is an easy process that happens everywhere suitable conditions exist, or an extremely rare event that only occurs under very special circumstances. On Earth, fossil evidence shows that life appeared quite early, about 3.5 to 4 billion years ago, almost immediately after the planet stabilized enough to maintain liquid water. And this might make you think that life forms easily, but this is a common mistake, because you are looking at a single sample, and from a single sample you cannot infer probability. Life may have appeared quickly because it is easy, but it could also have appeared quickly because if it had not appeared quickly, we would not be here to observe it. This is called observer bias, and it makes evaluating this first step extremely difficult. But suppose that step has occurred, that you have single-celled organisms existing in the oceans. You still have a very long way to go. For billions of years, life on Earth barely changed significantly in terms of complexity. Single-celled organisms existed, evolved slowly, but there was no explosion of diversity or structure. And then, about 600 million years ago, in what we call the Cambrian explosion, you see the relatively rapid appearance of complex multicellular life forms with organs, nervous systems, and clear body structures. This was a major leap, and like abiogenesis, we do not fully understand what triggered it. There are hypotheses about oxygen levels in the atmosphere, about biological interactions between species, about environmental changes, but there is no definitive answer. And that means this step could also be a filter. Maybe billions of planets have single-celled life, but very few of them cross the threshold to become complex multicellular organisms. Next, you have the evolution of complex nervous systems and behavior, and finally, intelligence. But even here, you need to be careful, because intelligence is not an inevitable destination. For most of the history of life on Earth, no creature developed intelligence at the level we see in humans. Dinosaurs existed for more than 160 million years, and throughout that time, there was no sign that they were heading toward a technological civilization. This shows that intelligence is not an inevitable result of evolution, but maybe a rare branch that occurs under very specific conditions. And even when intelligence appears, it does not guarantee that it will lead to technology. Modern humans with language and abstract thinking have only existed for about 200,000 years, and technological civilization, the kind that can broadcast radio and change the environment on a large scale, has only existed for the past few hundred years, an extremely small period compared to the history of life. When you put all these steps together, you start to see the picture more clearly. You are no longer looking at life as a single phenomenon, but as a chain of steps, each with its own probability. And if any one of these steps is extremely difficult, then the entire chain becomes rare. You don't need all the steps to be rare. You only need one step to be difficult enough to reduce the number of civilizations to a level where we may never see them. And this is the power of the great filter idea. It does not require you to identify exactly which step is difficult. It only requires you to accept that at least one step is like that. And when you return to the original question, you begin to see how this idea resolves the contradiction. If most planets fail at one of these steps, then the number of civilizations that reach the technological stage will be very small, possibly small enough that within the range we can observe, we don't see anyone. This does not mean that life does not exist, but that it rarely progresses far enough to become visible on an astronomical scale. And that explains why the universe could be full of worlds with simple life, but still look completely silent to us. When you look back at the history of Earth, you see a timeline stretching over billions of years, in which most of the time there was nothing resembling intelligence or technology. Single-celled life appeared quite early, but it was almost stuck in that state for an enormous period of time, nearly 3 billion years, before any leap in complexity occurred. Multicellular organisms, which we consider the foundation for the development of complex ecosystems, only appeared relatively late, about 600 million years ago, and even after that, it took hundreds of millions more years to have life forms sophisticated enough to develop complex nervous systems, flexible behavior, and finally, intelligence. When you look at this entire chain, you begin to realize that each step not only takes time, but can also be extremely difficult. And that means the chance that all these steps occur in succession on the same planet may be a very rare event. In this view, Earth is not a typical example, but an exception. There may be many planets in the universe with similar physical conditions, liquid water, atmospheres, energy from their star, but that does not guarantee that they will go through the entire evolutionary chain to the point of having technological intelligence. Most of them may stop at the level of bacteria or simple organisms, and never overcome the difficult steps such as the appearance of eukaryotic cells, multicellular organisms, or complex nervous systems. If even one of these steps is extremely rare, then the entire chain becomes rare, and the number of planets that reach the stage we can call civilization will drop very quickly. When you put this into the context of the universe, you may begin to see a different picture. Not a universe that is completely empty, but one that is full of worlds where life exists at a simple level, but very few of them advance further. Planets with bacteria, with single-celled organisms, or even with simple multicellular life forms may exist in many places, but the places where all those rare steps occur in succession to create technological intelligence may be extremely few. And if that is true, then the fact that we don't see any other civilizations is no longer so difficult to understand, because their number may simply be too small to be easily detected within the space we have observed. This leads to a conclusion that, in a way, is quite reassuring. If the filter is behind us, if the hardest steps have already happened, then our future may not be threatened by the same mechanism that stopped other civilizations. We don't need to worry that some invisible wall is waiting ahead to block our development, because we have already passed the hardest part of the journey. In this scenario, the silence of the universe is not a sign of an approaching danger, but a sign of an extremely harsh past that we have been lucky enough to overcome. However, even in this optimistic scenario, there is one thing you cannot overlook, and that is the meaning of rarity. If technological intelligence is truly so rare that we are one of the very few cases in the entire galaxy, or even in the entire universe, then that puts us in a very special position. It means that what we do and the decisions we make may have importance far beyond what we usually think. Not in a vague philosophical sense, but in a very concrete sense. If there are very few civilizations capable of understanding the universe, then each such civilization carries a portion of the cognitive capacity of the universe. Therefore, in this view, the silence is no longer something frightening, but a reminder. It says that the path from inanimate matter to intelligence is a long and difficult one, and the fact that we are here, capable of asking these questions, may be the result of an extremely rare chain of events. The fact that we have existed up to the present moment is not a sign that we have overcome the greatest challenge, but only that we have not yet encountered it. When you look at the history of Earth, you see a system that appears stable over long periods, but is also interrupted by extreme events that can completely change the trajectory of life. About 66 million years ago, an asteroid struck Earth and caused one of the largest mass extinction events, wiping out most species, including the dinosaurs, creatures that had dominated the planet for more than 160 million years. And if that event had not occurred, humans would very likely never have existed. This shows that evolution is not a stable linear process, but a series of stages interrupted by major events, and those events can happen at any time. When you expand that idea beyond Earth, you see that planets do not exist in safe isolation, but are located in a risky cosmic environment where supernova explosions can release enormous energy. Gamma-ray bursts can irradiate entire planets, and gravitational interactions can alter the orbits of celestial bodies in unpredictable ways. These events may be rare, but when considered on a scale of billions of years and billions of planets, they become factors that cannot be ignored. And any civilization that develops in that environment must face risks it cannot fully control. But the danger does not only come from outside, because when a civilization develops technology, it also creates new risks from its own activities. And this is the part you cannot overlook if you want to fully understand the issue. Technology allows control of energy and matter at increasingly higher levels, but at the same time, it opens up the possibility of causing consequences that could not have happened before. From large-scale wars to mistakes in manipulating biological or environmental systems. When you have more power, you also have more ways to make mistakes, and if those mistakes are big enough, they can end an entire civilization. What is important here is that you don't need an event that is certain to happen. You only need a small probability that repeats over time. Because if every civilization has a small probability each year of encountering an irrecoverable disaster, then over time, the probability that they will last long enough to reach the interstellar stage will gradually decrease. And if the time required to develop interstellar technology is very long, then most civilizations may never reach that point. They may exist for thousands or millions of years, but ultimately stop before they can leave traces that we can detect. In this scenario, the silence of the universe is not a sign of initial rarity, but the result of a continuous filtering process that occurs over time, where civilizations appear, exist for a period, and then disappear before they can expand on a large scale. This explains why we do not see ancient civilizations that have spread throughout the galaxy, because such civilizations may not exist, not because they could not form, but because they could not maintain their existence long enough. And this is the part that makes this scenario more frightening than any other, because if the filter is ahead of us, then the silence we observe is not a distant, unrelated phenomenon, but a signal with direct meaning for us. It says that there is some limit that civilizations usually cannot overcome, and we do not yet know what that limit is. It could be a physical risk, a biological risk, a technological risk, or a combination of many factors. But if it is strong enough to stop most other civilizations, then there is no reason to think that we are immune to it. This forces you to look at the future in a completely different way. Not as a straight line of continuous progress, but as a path that may contain breaking points and dangerous thresholds where, if crossed the wrong way, the system can collapse. If you accept that the filter may be ahead of us, then you need to look directly at a very specific and very uncomfortable possibility. That technology itself, which we often see as the path of progress, may simultaneously be the mechanism that causes civilizations to end themselves. And the history of our own species has shown how this begins. In 1945, humans first used nuclear weapons in the atomic bombings of Hiroshima and Nagasaki, marking the moment when a biological species gained the ability to destroy itself on a planetary scale. Before that point, every threat to life came from outside asteroids, natural climate change, or astronomical processes. But from that moment onward, the greatest danger began to come from within the system itself. Not because humans wanted to self-destruct, but because when you gain the ability to control energy at a sufficiently high level, you also gain the ability to cause consequences beyond your control. And this does not stop at nuclear weapons. It is only the beginning of a broader trend. When you look at the trajectory of science and technology, you see a clear accelerating curve in which we are increasingly able to manipulate the world at deeper levels, from matter to information, from biology to intelligence. And this brings enormous benefits, but at the same time opens up new risks that did not exist before. For example, the rapid development of artificial intelligence in the 21st century, where systems are becoming increasingly complex, capable of processing information on a large scale, making decisions, and operating in ways that even their creators do not fully understand. And this does not mean that artificial intelligence will definitely become a threat, but it shows an important trend. We are building increasingly powerful systems while our ability to predict and control their consequences is not increasing accordingly. And if you place that in the context of a civilization where many such systems interact with one another, you can begin to see how small risks can accumulate into large ones. Similarly, in the field of biology, technologies like CRISPR allow direct intervention in genetic code, opening up the possibility of curing diseases and gaining deeper understanding of life, but at the same time creating the possibility of deliberately or accidentally designing biological agents that can cause large-scale consequences. And what is important is that none of these factors need to be certain to happen in order to become part of the filter, because you don't need a civilization to definitely self-destruct. You only need a small but existing probability. And when you combine that with time, the overall probability that that civilization will last long enough to reach the interstellar stage begins to decrease. If each year or each generation has a small chance that some technology will lead to an irrecoverable event, then over time it becomes almost certain that such an event will occur. And this is how complex systems often fail, not through a single predictable event, but through the accumulation of small risks leading to a breaking point. When you look at this on a larger scale, you begin to realize that technological development is not a straight upward line, but a process in which capability and risk increase together. Each step forward opens new opportunities, but also opens new ways for the system to fail. And if there is no sufficiently strong stabilizing mechanism to manage those risks over long periods, then the system can become increasingly fragile, even though on the surface it appears stronger. This leads to an important paradox. The civilizations that advance the furthest technologically may be the ones facing the greatest risks, because they have more ability to intervene in systems they do not yet fully understand. And in the context of the paradox we are considering, this provides a direct explanation for the silence of the universe, not because civilizations do not appear, but because they do not last long enough. They reach a certain level of technology where the ability to cause a terminal event begins to increase. And although some may last longer or manage risks better, the general trend may still be the same, making the number of civilizations that last long enough to spread across the galaxy extremely small. According to Albert Einstein's theory of relativity, the speed of light in a vacuum, about 299,797 kilometers per second, is not just a large number, but the absolute maximum limit for any form of information transmission and motion, meaning no signal and no object can exceed it. This may not seem too serious if you only think within the scale of Earth, but when you expand it to the scale of the universe, you begin to see its consequences become extremely clear. The distance between stars is not measured in kilometers or millions of kilometers, but in light years, the unit of distance that light takes 1 year to travel. and even the nearest star to us besides the Sun, Proxima Centauri, is about 4.2 light years away. That means if you send a radio signal today, you would have to wait more than 4 years for it to arrive, and another 4 years to receive a reply, assuming there is someone there to reply. And this is only the closest case. Within the same galaxy, distances can reach thousands or even tens of thousands of light years. And when you go beyond the galaxy, you are talking about millions or billions of light years. At those distances, communication is not only slow but almost loses practical meaning, because a simple exchange of information could take tens of thousands of years, far exceeding the lifetime of any civilization we can imagine. Not only communication, but travel is also limited by the same law. Even if you have technology advanced enough to reach a significant fraction at the speed of light, journeys between star systems would still take years, centuries, or longer. And that raises problems not only of energy, but also of biology, psychology, and social organization. A civilization may be able to send probes, but building a connected network between star systems becomes extremely difficult when each link is stretched over time to the point where effective coordination is no longer possible. And if you think that a sufficiently advanced civilization could overcome these limits, and you must remember that the speed of light limit is not a temporary technological obstacle, but a consequence of the structure of space-time, a thing that, according to our current understanding, cannot be broken. When you put this into the context of the paradox we are discussing, you begin to see another explanation for the silence of the universe. An explanation that has nothing to do with whether life is rare or whether civilizations self-destruct, but simply that they cannot communicate with one another effectively. Each civilization may exist in its own bubble, limited by the speed of light, unable to know about the existence of other civilizations unless they are very close to each other on a cosmic scale. And even if they discover one another, maintaining a meaningful exchange of information remains a major challenge. This creates a universe where civilizations may exist simultaneously but still remain completely isolated, like islands separated by oceans that cannot be crossed. And this also has another important consequence. Even if a civilization develops technology and exists for a long time, their traces may not spread fast enough to be detected before they disappear. A radio signal may take thousands of years to reach us, and if the civilization that sent that signal only existed for a few hundred or a few thousand years, then the chance that we received a signal during exactly the time they are existing is very small. This creates a kind of asynchrony in the universe, where civilizations can appear and disappear without ever matching up in time to recognize one another. When you look at the entire picture, you begin to see that even in the most optimistic case where life is not too rare, and civilizations do not self-destruct immediately, the laws of physics can still create a very high degree of isolation, not because there is an intentional barrier, but because of the way space and time are structured. This does not mean that communication is completely impossible, but it does mean that it is extremely difficult, extremely slow, and dependent on very specific conditions that may rarely occur. And when you combine this with all the other factors we have discussed, from the rarity of evolutionary steps to the risk of self-destruction, you begin to see a more consistent picture of why the universe may appear so silent, not because there is a single explanation, but because there are multiple layers of barriers stacked on top of one another, each reducing the chance that civilizations will connect with one another. And in that picture, the physical limit plays a very fundamental role, because it cannot be changed or avoided. It is the foundation that everything else must follow. When the speed of light is the absolute limit, everything you know about the universe is limited by the distance that information can travel to you within a certain amount of time. And that means that even if other civilizations exist, you can only know about them if they are close enough, and if their signals are strong enough and last long enough to reach you. But in reality, this rarely happens. The distances between star systems, between regions in the galaxy, and especially between galaxies, are so large that each civilization can live out its entire lifetime without ever receiving a single signal from outside. Not because there is no one else, but because the information cannot arrive in time. This leads to a very specific consequence. There is no instantaneous communication in the universe. You cannot ask a question and receive an answer in a reasonable amount of time, if the other party is hundreds or thousands of light years away from you. Every interaction is stretched out over time to the point where the concept of dialogue almost loses its meaning. If you send a signal today and have to wait hundreds of years to receive a response, then in practical terms, you're not communicating. You're sending a message into a system whose existence you do not even know. And the answer, if it comes, will arrive at a time when you are no longer there to receive it. This completely changes the way you think about communication, because it is no longer a continuous two-way process, but becomes a series of discrete, asynchronous signals that are extremely difficult to coordinate. This isolation applies not only to information, but also to any form of support or physical interaction. There is no way for another civilization to come help if a system runs into trouble. No rescue capability, no timely intervention. If a planet faces a disaster, whether natural or caused by themselves, they must solve it themselves or fail to solve it, because any help from outside, if it exists, will arrive too late to make a difference. This makes each civilization a closed system, where all decisions and consequences take place within a space that has no outside intervention. You can imagine this as being completely trapped in deep space, not in the simple physical sense, but in the sense of information and existence. You can see the light from distant stars. You can measure and analyze the universe, but you cannot touch it in any meaningful way, and it cannot touch you within a time frame that matches your own existence. You exist in your own separate present, and everything outside is only signals from the past images of things that happened long before you existed. And this is not only true for us, but may be true for every other civilization as well. Each civilization is a small point of light in space, radiating its own signals, but rarely intersecting with the signals of other points. When you look at the universe this way, the silence begins to take on a different meaning. It does not necessarily mean that there is no one, but it may mean that there is no one within the range where we can connect. No one close enough, long-lasting enough, and synchronized enough in time to create an interaction that we can recognize. Civilizations may appear, exist, and disappear within their own separate bubbles, and only in extremely rare cases do two of these bubbles overlap enough to produce a signal that can be received and confirmed. And this also explains why even weak or rare signals are still difficult for us to confirm. A signal may come from a civilization that ceased to exist long ago, or from a system that we cannot observe again to verify. There is no way to establish a stable communication channel, no easy way to confirm repetition, and this makes distinguishing between natural signals and artificial signals extremely difficult. When you put all of this together, you begin to see that isolation is not a minor detail, but a fundamental feature of the universe. It is not a temporary barrier that technology can overcome, but a consequence of the way space and time are structured. And if that is true, then the silence we observe is not something unusual, but something you should expect. A universe where civilizations exist but cannot easily connect will look very much like an empty universe, at least from the perspective of any individual civilization. And even if you assume that a civilization could overcome informational isolation and accept communication time stretching across centuries or millennia, they would still face another barrier that is much more directly physical. The space environment, itself an environment that, if you look at it straight without romanticizing it, is almost completely hostile to life as we know it. Space is not an ocean you can swim across. It is near perfect vacuum where there is no pressure, no air, and no natural mechanisms to support biology. That means any form of life that evolved on a planet like Earth must carry its entire life support system if it wants to survive out there. That even if you can create an artificial environment, you still cannot eliminate another factor that is far more important: cosmic radiation. Outside the protection of an atmosphere and magnetic field, living organisms are directly exposed to high-energy particles from the sun and from more distant sources like supernovae. And these particles can penetrate biological tissue, damage DNA, increase the risk of cancer, and even affect the nervous system in ways we still do not fully understand. On Earth, the magnetic field acts as a shield, deflecting most of these charged particles, and the atmosphere absorbs the rest. But in deep space, those protective layers do not exist. And any system that wants to protect life must recreate them with technology. This is not only difficult, but also extremely energy and resource intensive. But radiation is only part of the problem. Even in a microgravity environment where there is no significant gravitational force, the human body begins to change in ways you cannot ignore. Astronauts on space stations have shown that after just a few months, muscles start to atrophy, bone density decreases, the cardiovascular system changes, and even the immune system is affected. This is not a minor detail, but a sign that our biology is finely tuned to function under Earth's conditions, with gravity, pressure, and a stable environment. When you remove those factors, the body no longer functions the way it evolved to. And if you extend this over years, decades, or generations, you are talking about profound biological changes that we do not fully understand and do not yet know how to control. This leads to an important realization. Humans, and perhaps any intelligent life form that develops on a planet, are not a general-purpose system that can function anywhere, but a system optimized for a very specific environment. On Earth, everything from air pressure, atmospheric composition, temperature, to the level of radiation falls within a range where life can exist and thrive. When you leave that range, you do not just face difficulties. You step into an environment where everything works against you. And this does not only apply to humans, but may apply to any other form of life as well, because evolution always occurs in a specific context. And the traits that help a species survive in that environment do not necessarily help it survive in another. When you put this into the context of expansion into space, you begin to see a very real barrier. Even if a civilization develops technology advanced enough to leave its planet, maintaining life in space for long periods is an extremely large challenge. You need energy to create habitable environments. You need materials to protect against radiation. You need systems to maintain biology. And you need to solve problems that we do not even fully understand yet. This does not mean that expansion is impossible, but it does mean that it is not a natural or easy step. It requires a very high level of control and stability, and any mistake can lead to serious consequences. And this is where the issue becomes important for the paradox we are considering. Even if a civilization does not self-destruct, even if they overcome technological risks and last long enough, they still face a hostile cosmic environment where expansion is not the default but a major challenge. This can slow down or even prevent the spread of civilizations, keeping them within their own star systems for long periods, and therefore reducing the chance that they leave traces on a scale that we can observe. When you put all of this together, you begin to see that space is not just empty space between the stars, but an active barrier to life. It does not support, does not protect, and does not easily allow long-term existence without continuous technological intervention. And that means that any civilization that wants to overcome this barrier must reach a very high level of development and maintain it for a long time, a thing that, as we have seen, is not easy. Therefore, when you look at the silence of the universe from this angle, you may begin to see part of the explanation. It is not that civilizations do not exist, but that they are limited not only by distance and time, but also by the very environment they must overcome. And if that environment is harsh enough and difficult enough to conquer, then the number of civilizations that can truly expand beyond their own planet and become visible will be very small. This does not completely rule out their existence, but it makes their presence rare and hard to detect. And in such a universe, silence is no longer surprising, but a natural consequence of the limits that life must face. All the barriers we have just gone through, from distance, time, radiation, to the harsh environment of space, lead you to a broader realization. A realization that is not comfortable but is very consistent with the way science views the world. The universe is not designed for us. There is no sign that the laws of physics exist to serve life, and even less sign that they are fine-tuned to favor any particular species. Those laws simply exist, and every system, from fundamental particles to galaxies, must strictly obey them. This means that life, if it exists, is not the goal of the universe, but only a possible outcome under some very specific conditions. When you look in this direction, you begin to see that our existence is not proof that the universe is aimed at life, but only an example that in a system large enough and complex enough, rare outcomes can still occur. This idea is not new. It can be traced back at least to Nicolaus Copernicus and the Copernican principle that Earth is not the center of the universe. And over time, this principle has been expanded into a more general view. We are not in a special position, not in space, not in time, and perhaps not in nature either. When you look at our position in the Milky Way, you see that we are not at the center, but in a relatively ordinary spiral arm. When you look at the solar system, you see that it is one of billions of star systems with no standout features on an astronomical scale. And when you look at the history of Earth, you see that life existed for billions of years before humans appeared, and may continue to exist in other forms after we disappear. This leads to a conclusion that seems simple but is actually very profound. There is no reason to assume that we are the center of anything, not in space, not in time, and not in the structure of reality. The laws of physics do not care whether we exist or not. They do not change to help us survive, and they do not provide any special protection. If a planet is struck by an asteroid, the laws of physics do not intervene to stop it. If a civilization destroys itself through its own technology, there is no natural mechanism that guarantees it will not happen. Everything proceeds according to rules we can describe but cannot negotiate. When you put this into the context of everything we have discussed, from the rarity of evolutionary steps to technological risks and physical limits, you begin to see that our existence may not be a sign of something special, but the result of a chain of random events occurring in a system large enough to allow such chains to happen. This does not diminish the value of our existence, but it changes the way you perceive it. Instead of seeing it as something inevitable, you begin to see it as something that might not have happened, a result that was not guaranteed, a case that, if you ran the history of the universe many times, might not repeat. And this brings you to a different state of mind, a state that is not completely pessimistic, but also not simply optimistic. It is a profound neutrality where you accept that the universe has no obligation to contain life, no obligation to sustain life, and no obligation to allow life to expand or communicate. If life exists, it exists under very specific conditions, and if those conditions change, life can disappear without leaving a trace. This makes the silence of the universe more understandable, not as something abnormal that needs a special explanation, but as a natural consequence of a system where nothing is prioritized. But at the same time, it also raises a question you cannot easily dismiss. If we are not special, if we are only one of many possible outcomes, then why are we here to ask these questions? Expanding that perspective further, you encounter an idea that is not based on physical limits or evolutionary probability, but on the behavior and logic of intelligent systems. An idea called the dark forest hypothesis. And although it is not a scientific theory in the strict sense, it fits surprisingly well with what we observe, because it starts from a very simple assumption. Every intelligent civilization has the basic goal of survival, and in a universe where information is severely limited by distance and the speed of light, where you cannot know for sure the intentions of any other civilization, then every entity outside your own could be a potential threat. Not because they are definitely hostile, but because you have no way to verify the opposite before it is too late. And in a system where the consequences of a mistake can be absolute, that is, the end of the entire civilization, then assuming the lowest risk becomes the most rational strategy. Imagine the universe as a dark forest, where every creature moves in silence, not knowing what is around it, unable to see far, unable to communicate quickly, and with no way to check the intentions of other creatures. In such an environment, making noise is not a neutral act, but a risky one, because any sound you make could reveal your location to an entity you do not want to meet. And if that entity is capable of harm, you will not get a second chance to correct your mistake. When you transfer that logic to the universe, you begin to see that broadcasting strong signals into space is not just communication, but self-revelation. You are saying, "I am here," to anyone capable of listening, and you cannot choose the recipients, cannot control their reaction, and cannot know whether they have technology far beyond yours. This turns an apparently harmless action into a high-risk strategic decision. In a universe where civilizations millions of years ahead may exist, the technological gap could be so large that any interaction would be asymmetrical And in that situation, the safest course is not to seek attention but to avoid it. This leads to a very specific consequence. Civilizations, if they exist, may choose silence not because they lack the ability to communicate, but because they have reason not to do so. They may observe the universe, collect data, and even recognize the existence of other civilizations, but still decide not to send signals, because the benefits of communication are not great enough to outweigh the potential risks. This could also explain why we do not see large-scale technological signatures, because a civilization aware of the risks may try to minimize its own traces, avoid activities that create easily detectable signals, and maintain a level of invisibility in the cosmic environment, not because they cannot do bigger things, but because they do not want to be noticed. When you place this alongside all the other factors we have discussed, from the rarity of life, technological risks, to physical limits and informational isolation, you begin to see that there are many different paths leading to the same outcome, a universe that looks silent from the perspective of any individual civilization. And the dark forest is only one of the mechanisms that may contribute to that picture. What makes this idea worth thinking about is not that it is certainly correct, but that it forces you to reconsider our own behavior, because if broadcasting signals truly carries risk, then our attempt to listen may be a much safer strategy than trying to speak. And that raises a question we have not really answered. In a universe we do not fully understand, is silence a sign of absence, or is it a sign of caution? And if the answer is the latter, then the silence we are observing is not a meaningless void, but a deliberate choice by systems that want to continue existing. Looking back at the entire argument, one detail begins to stand out in a completely different way. We are not only listening to the universe, we have been and are sending signals into it for a much longer time than most people realize. Right from the early 20th century, when radio technology began to develop, Earth became a source of electromagnetic broadcasts, from radio programs and television to radar signals. And these signals do not stop at the atmosphere. They spread into space at the speed of light, forming an expanding signal bubble moving outward from the planet. Over time, that bubble has reached a radius of tens or even hundreds of light years, meaning that any civilization within that range, if they have sensitive enough equipment and are listening, could in principle detect our existence. And this is not just an unintentional process. In some cases, we have deliberately sent messages. A prominent example is the Arecibo message sent in 1974 from the Arecibo Observatory toward the M13 globular cluster, a coded message containing information about mathematics, the structure of DNA, and our location in the galaxy. This was not a practical communication effort in the sense of expecting a reply, because the distance to M13 is about 25,000 light years, but it is a clear symbol showing that we are willing to reveal our own existence. When you place this action in the context of what we have just discussed, especially the idea of a universe where civilizations may choose silence to avoid risk, you begin to see a question emerge that previously may not have seemed so important. Broadcasting signals is no longer just an expression of curiosity or the desire to connect, but becomes a decision with consequences. Every signal we send carries information not only about our structure, but also about our existence. And although the large distances make receiving the signal difficult, it is not impossible for a sufficiently advanced civilization. This means that, whether intentionally or not, we have begun to participate in a process we do not fully understand. You might say that the probability of someone being close enough to receive the signal is very small, and that may be true, but this is exactly the kind of argument we have encountered before. A small probability does not mean zero, and when you combine it with time and scale, low probability events can still occur. A signal sent today may take tens, hundreds, or thousands of years to reach somewhere, and any reply, if there is one, will take the same amount of time to return. This means we are participating in a long-term process whose outcome may occur in a very distant future, beyond our direct observation. What is noteworthy is that while we began sending signals unconsciously long ago, the intentional sending of messages remains a controversial topic in the scientific community. Some argue that actively making contact is the next natural step, a way to expand our understanding of the universe, while others warn that we do not have enough information to assess the risks. in a universe where we do not yet know if anyone else exists. Revealing our location may be harmless, but it may also not be. And the problem is that we have no data to distinguish between those two possibilities. When you think about this in the context of the dark forest hypothesis, the question becomes clearer. If other civilizations exist and have chosen silence as a survival strategy, then our actions may run counter to that strategy. We are not only silent, we are speaking, and not just speaking, but speaking more and more clearly as our technology advances. This is not necessarily wrong, but it is a choice. And like every choice in an uncertain system, it comes with consequences we cannot yet predict. What is interesting is that even if you set aside all concerns about risk, broadcasting signals still raises a more fundamental question about our goals. What are we trying to achieve? Are we looking for proof that we are not alone, or are we trying to establish some form of real communication? Because these two goals are not the same, and the methods to achieve them are also different. Listening is a passive act that allows us to gather information without interfering with the system, while broadcasting is an active act that changes the state of the system in a way we cannot reverse. When you look at the entire picture from the fact that we have been broadcasting signals for more than a century to deliberate efforts like the Arecibo message, you begin to see that we have crossed a boundary, even if we may not have fully realized it. We are no longer just passive observers of the universe, but have become part of the interaction process, even if that process may stretch across thousands of years. From that perspective, the issue no longer stops at pure science, but turns into an ethical question, a question we cannot avoid with data or equations, because it relates directly to how we choose to act in a universe we do not fully understand. Should we continue searching, continue listening, and more importantly, should we actively make contact or not? This is no longer a question of capability, but a question of choice. On one hand, the desire to explore is a core part of science, a driving force that has taken us from simple observations to understanding the structure of the atom, from looking up at the sky to setting foot on the moon, and by that logic, the search for life beyond Earth seems like the next natural step. It is not just curiosity, but part of the effort to understand our place in the universe, a question that has existed long before modern science. But on the other hand, when you place that in the context of the risks we have discussed, from the possibility of self-destruction to physical limits and potential survival strategies of other civilizations actively, broadcasting signals is no longer a neutral act, but becomes a decision that could affect the entire future of humanity. The tension here lies in weighing two very different values: the value of knowledge and the value of existence. Science often assumes that knowing more is always good, that collecting information and expanding understanding is a goal worth pursuing. But in this case, seeking information may be equivalent to revealing information about ourselves. This creates a paradox. To know whether there is anyone else out there, we may need to do things that could draw attention to us, and that attention may carry risks we cannot yet evaluate. This is not a situation where you can simply apply familiar principles of science, because the potential consequences are not just right or wrong, but possibly existence or non-existence. Another factor that makes this question more complex is its scale. This is not an individual decision, nor is it a decision for a single nation or a small group of scientists. Any action involving strong signals broadcast into space would, in principle, affect all of humanity, and even the future of humanity. This raises a problem of responsibility. Who has the right to make that decision? And on what basis? In history, many major scientific advances have been made by small groups, but in this case, the scope of the consequences may be much larger than the scope of those making the decision. You can also look at this issue from another angle: uncertainty. We do not know if anyone else is out there. We do not know what they are like, and we do not know how they would react if they learned of our existence. In some cases, science can proceed under uncertainty because the risks are acceptable or can be controlled. But here, the level of uncertainty combined with the scale of the consequences makes evaluation much more difficult. There is no model we can use to predict exactly what will happen, and that means any decision must be made under conditions of incomplete information. This leads to a conclusion that may not be satisfying but is honest with the reality of the issue. There is no simple answer. There is no argument strong enough to completely eliminate one side of the problem. Continuing the search may lead to profound discoveries about the universe and our place in it. But actively making contact may carry risks we do not yet fully understand. Conversely, remaining silent may reduce risks, but it may also slow down or even prevent one of the most important discoveries we could make. And perhaps the most important thing here is not to provide a definitive answer, but to recognize that this is a question we need to think about seriously, not as an abstract idea, but as a practical issue that could affect our long-term future. This does not mean we should stop, nor does it mean we should continue without thinking, but it means we need to understand more clearly what we are doing and what we may face. So instead of ending with a clear conclusion, it may be more reasonable to leave that question open, not because we do not want to answer it, but because we do not yet have enough information to do so with certainty. Going back to the original question, the seemingly simple question that Enrico Fermi asked, where is everybody? But this time not looking at it as an absence that needs to be filled, but as a sign that needs to be explained. You may begin to see that perhaps the very way we ask the question is the problem. Instead of asking why we do not see them, perhaps the better question is what happened to them. They may have existed possibly in many places, possibly at different times in the history of the universe, but they no longer exist at the moment we are observing. When you frame the question that way, the silence is no longer an incomprehensible void, but becomes a predictable outcome from a series of mechanisms we have examined. Life may be rare, but not rare enough to never happen. Evolutionary steps may be difficult, but not impossible to overcome. Civilizations may appear, but not last long enough. Technology may develop, but at the same time create self-destruction risks. Physical limits may prevent expansion and communication. The space environment may slow down or completely block the spreading process. And even if all of that is not enough, survival strategies like those in the dark forest hypothesis may cause civilizations to choose silence as a rational option. When you combine all these factors together, you begin to see that no single explanation is needed to create the silence, but rather many factors acting at once, each reducing part of the chance that we will detect other civilizations, until the final result is a universe that looks empty from our perspective. This also changes the way you look at the role of intelligence. The problem is not whether we are smart enough to search, because we have already developed tools, methods, and theories strong enough to begin exploring these questions. The problem lies in the fact that the reality we are trying to understand may not be structured in the way our intuition expects. A system may have many components, each one reasonable on its own, but when combined, they produce a result that none of the components could predict alone. This leads to an important shift in how you view this paradox. It is no longer a simple contradiction between expectation and observation, but a sign that there are many layers of complexity in the system that we do not yet fully understand. Life may exist but be rare. Intelligence may appear but not be stable. Technology may develop but be dangerous. Communication may be possible but not practical. Civilizations may want to communicate but choose not to. Each of these possibilities does not exclude the others, and when you combine them, you get a picture in which silence is not only possible, but a natural outcome. And when you look at that picture, the question, where is everybody, begins to lose its original meaning. It is no longer a question about location, but a question about process. It is no longer about finding a point in space, but about trying to understand a sequence of events in time. And in that sequence, there may have been many civilizations that appeared, existed for some period, reached a certain level of development, and then disappeared. Without leaving traces, we can easily recognize. This does not make the universe less interesting. On the contrary, it makes it more complex, and in a way, more thought-provoking. Because instead of an empty universe or a universe full of easily observable life, you are facing a universe where life, intelligence, and technology may be temporary phenomena, appearing and disappearing according to rules we have only just begun to understand. And in that context, silence is not absence, but part of the structure. Therefore, when you prepare to reach a conclusion, perhaps what is important is not finding a single answer to this paradox, but realizing that the original question may need to be changed. Not why don't we see anyone, but what happened to those who might have been there, and more importantly, which of those mechanisms might apply to us. Because when you shift the question from space to time, from location to process, you are not only trying to understand the universe, but also trying to understand your own place in a system that may not work the way we expect. Everything we have just gone through ultimately returns to a very simple but not easy to accept point. The silence of the universe is not a subjective impression, but a real phenomenon, a fact that any explanation must confront. We have looked at the numbers, at the scale of the universe, at the number of stars and planets, and by basic logic, everything leads to an expectation that life, even intelligent life, should not be rare. We have looked at observational reality, at data from search programs, and seen that there are no confirmed signals, no clear traces, no direct evidence. We have considered different possibilities, from the rarity of evolutionary steps to technological risks, to physical and environmental limits, to even survival strategies that may cause civilizations to choose silence. And when you put all of that together, you do not arrive at a single answer, but at a set of possibilities, each reasonable in its own way. But among all those possibilities, two main directions stand out, and neither is comfortable. One is that we are truly alone, not in an absolute sense that can be proven, but in the practical sense that within the range we can observe, no other civilizations exist. This could happen if the steps required to create technological intelligence are extremely rare, if the filter is behind us, and we are the result of a chain of events that is almost impossible to repeat. The second possibility is that civilizations do not last long enough, that they appear, develop, and then disappear before they can spread or leave traces we can detect. This could happen if the filter is ahead of us, if there are risks that most systems cannot overcome, whether due to technology, the environment, or any other factor. What is noteworthy is that both of these possibilities are frightening, but in different ways. The first possibility brings a kind of cosmic loneliness, where we are not just a small part of a large system, but possibly one of the very few, or even the only, places where the universe becomes aware of itself. The second possibility brings another kind of unease, where we are not the exception, but part of a common process, a process whose usual outcome is an end before reaching a long-term stable state. One side says we are rare, the other says we are fragile, and neither offers real comfort. This leads to a realization that may not be intuitive, but fits with the way science often progresses. The universe has no obligation to be understandable to us. The laws of physics we discover are not designed to fit human intuition, and their consequences do not need to make sense in the way we expect. When you look at the history of science from Earth not being the center, to time and space not being absolute, each advance has required us to abandon part of our intuition to accept a broader and often less intuitive picture. This paradox may simply be the next step in that process, a sign that there are aspects of the universe we do not yet fully understand. And perhaps this is the most important point, to stop it not with an answer, but with a different way of looking. The silence of the universe is not only a question about what is out there, but a question about our place in the entire system. It forces us to consider the possibility that we are not the center, not the goal, and not the inevitable result. It forces us to think about our existence as part of a larger process that may be rare, may be fragile, and may not last forever. Understanding that does not make the universe less awe-inspiring. On the contrary, it makes it more profound, because it shows that even in a system not designed for us, we still have the ability to observe, think, and ask questions about it. And when you look up at the night sky the next time, perhaps you will no longer see only distant points of light, but a vast system where silence is not a void, but part of the story we have only just begun to understand, and in which our place may be small, but not without meaning. If you find this perspective makes you think differently about the universe, please hit subscribe so you don't miss the next in-depth analyses. See you in the next video, where we continue exploring the mysteries that science still has no answers for.